Hello everyone. In this talk, I'll be discussing our project on utilizing bandits for adaptive batch selection in neural network training. While our research started with improving training efficiency in general, the algorithm we're presenting proved to be particularly effective in handling datasets with label noise. Training neural networks efficiently is increasingly relevant today as we deal with large-scale language and vision models that are very resource intensive. While pushing the boundaries of what's possible, training these models have been shown to contain redundancies. One of the key issues is training on large, often noisy datasets sourced from the web or crowdsourced, leading to low quality data. Improving training efficiency can be done in one of two ways. First, enhancing model efficiency can be done through techniques like knowledge distillation, architecture search, and hyperparameter tuning. Second, through optimizing data selection, either by pre-training on available data and identifying core sets of useful instances, or through online data selection, which continuously learns which data is most beneficial. Focusing on online data selection, we address the challenge of selecting the most useful data for each stage of training. A common approach in this case is adaptive batch selection. In adaptive batch selection, data instances are scored based on various metrics, and these scores inform training batches. The instances are weighted based on factors like difficulty or training importance. These weights can be heuristic based, like in curriculum learning, or learned through additional models. The goal is to adaptively refine these weights based on training feedback. The data instances are first ranked based on their weights, and top ones are chosen for training. One step of training is performed, after which we obtain feedback for the selected instances. The feedback is then used to adapt the original weights. Various weight metrics are used in the literature. Common examples include metrics inspired by curriculum learning, progression from easy to hard, or alternatively from hard to easy instances, like in hard example mining. Metrics can be defined directly based on the influence on the model or its performance, like the loss based on or gradient based metrics. The active learning techniques are also used, like using prediction uncertainty. Those have proven effective, especially for filtering out mislabeled data. Addressing noisy labels is crucial. Another common method for this is the small loss trick, where instances with larger losses are often mislabeled. Alternatively, one can use an additional model to learn the metric. However, that would be at a large cost to overall efficiency. Additionally, balancing exploration and exploitation is vital, for which we can apply strategies like epsilon greedy, Boltzmann distribution, or alternatively we can use bandit approaches. In this study, we focus on the latter, and particularly we choose bandit approaches that are useful in non-stationary environments, like neural network training is a non-stationary environment. In which case the underlying instance scores change over time. We started with the classic EXP3 adversarial bandit approach. Our main contribution lies in demonstrating the effectiveness of the combinatorial bandit, specifically the follow the preferred leader algorithm for joint batch selection. We show promising results on training with noisy labels in experiments with the CIFAR10 datasets under various noise levels. Our method consistently outperforms others across different noise ratios, with the performance gap widening as noise increases. This highlights the potential of adaptive batch selection using bandits in training neural networks effectively, even in the presence of label noise. In classic multi-arm bandit scenarios, we have k arms, each corresponding to a hidden probability distribution of potential rewards. Our goal is to maximize the cumulative reward by pooling highly rewarding arms. In our case, arms correspond to data instances, and our goal is to choose ones that are most informative. Adversarial bandits is a variant in which we don't assume a specific shape of the reward distribution. This is particularly useful when handling non-stationary problems, which is the case when we are training the neural networks. The EXP3, which stands for Exponential Weight Algorithm for Exploration and Exploitation, model works by associating weights with arms. In our case, those will be data instances, and adapting them over time, and forming a probability distribution over instances. For example, consider a scenario with 10 instances. We form a batch of size 2 by sampling from an empirical exponentially normalized probability distribution. After training our model on this selected batch, we obtain the instance scores based on their significance for training. On top of that, we perform an important sampling step in which we scale the obtained scores according to the probability of observing the particular instance. The scaled scores are then used to adjust weights associated with instances. Um, Various metrics in the literature can be used as weights. In our work, we focused on using prediction probability variance as a weight metrics, which was proven effective for learning with noisy labels. This involves saving the prediction probabilities for the correct class of each instance over time and computing their variance. High variance instances indicate how high variance indicates higher model uncertainty, making such instances prime candidates for selection. Next, we modify the original algorithm for combinatorial use, acknowledging that batch selection is inherently a combinatorial problem. The joint impact of batch and model on model differs from the sum of influences of individual instances. Directly applying EXP3 to combinatorial cases is impractical due to exponential scaling of the weight space with batch size. To address this, we use the follow the preferred leader algorithm, a combinatorial bandit known for its computational efficiency. It approximates the probability of each combination by associating weights with individual instances and employing geometric resampling. Geometric resampling is a Monte Carlo method that estimates how frequently a specific batch would be selected, informing the rarity and probability of occurrence for that batch. This probability is used to scale. This probability is used to scale the instance contributions within a batch. Depending on the number of samples, geometric resampling can be computationally intensive. However, it can be easily parallelized, making it a viable method in large-scale neural network training scenarios. Our experiment focused on training a 40-layer dense neural network on CFAR10 dataset. We varied label noise ratios across 6 different levels and adapted the learning rate during training in 3 multiplicative steps, which is a common practice for this model type. We compared 4 batch selection strategies: uniform, active bias, that uses the uncertainty metric directly, EXP3, and FPL. Both EXP3 and FPL incorporated the same uncertainty metric along with an exploration-exploitation balance. Upon analyzing the results from multiple runs across different noise levels, it is evident that our method, FPL, depicted in green, consistently outperformed others throughout the training for all noise ratios. Particularly in the final epoch, the disparity in performance widened with increased noise, highlighting the effectiveness of bandit methods, especially our approach in dealing with noisy labels. Next, we analyzed how weights changed over time and we found smooth adaptation throughout the training. Some weights increased, suggesting these instances were more useful for training, while others remained flat. About 40 epochs were required for the algorithm to visit each instance at least once, after which we observed a drop in entropy, indicating a gradual focus on specific subsets of instances. Then we analyzed the behavior of the algorithms throughout training by plotting the number of occurrences for each instance within each subsequent 10 epochs window. We sorted the instances by the number of their occurrences for clearer visualization. We observed that EXP3, marked in red, tends to overfit to a few instances on the left-hand side of the plot and treats other more equally, resembling an exponential distribution. In contrast, FPL acted more like a filter, retaining only about 20,000 informative instances towards the end of the training and sampling more equally across those. In fact, FPL has the inclination towards retaining informative instances towards the end of the training. Next, we aggregated the results from all the frames of the presented animation and overlaid them with percentage of mislabeled instances within 1000th instance sliding window from left to the right of the plot. By analyzing the occurrence of mislabeled instances, we found that both algorithms learned to pick mislabeled instances least frequently. However, EXP's free strategy is less effective as it continues to pick mislabeled instances for exploration purposes. In conclusion, our experiments demonstrate that integrating exploitation in batch selection significantly enhances performance. Comparing FPL with EXP3, we found that selecting batches based on their joint importance is more effective than selecting individual instances. While EXP3 tended to overexplore and focus on few instances only, FPL proved particularly efficient for learning with noisy labels, acting similarly to a data filter and converging smoothly throughout the training. Thank you everyone for attending my presentation.